Hello guys, welcome to today's video. My name is Daniel, and in this video I'll be talking about thermodynamics as a course and its application to real life situation. So the question here is, what is thermodynamics? Yes, as we all know, thermodynamics is a science that deals with the energy and its relation to matter. We go down to the laws of thermodynamics. From our previous knowledge, you know that law of thermodynamics states that is the first law of thermodynamics, states that energy can neither be created nor destroyed, but be converted from one form to another. So that is previous knowledge. So as we advance in colleges and our education, we get to know more about thermodynamics, and some more definitions pop out. So I have another definition here, which is more enticing and more straight to the point. So it goes this way. The first law of thermodynamics states that the internal energy of a closed system remains unchanged if the system is isolated from its surroundings. So what am I trying to say here? Say that the change in internal energy of a system is equal to whenever you add the heat and work done by the system. And remember that for a closed system, the sum of the work done is equal to the net heat taken away from the system. So that is thermodynamics. So how do we write this? So mathematically we are going to write this way. Mathematically this means that du plus w is equal to du. Yeah, sorry, it should be dq. Yes, it should be dq, right? So which implies that q plus w is u2 minus u1, which is the change in internal energy. Now others may decide to use this other one, which is q minus w, which is equal to u2 minus u1, but it's all the same thing. What matters there is the sign convention. Whichever one you are using, you stick to it. So why I decided to use plus instead of minus is because of this convention written down here. For this convention, q plus w is more practical because in steam engines, heat rejected by the system is denoted with a negative, and work done by the turbine or turbine work is always a negative work. So in order to stick to this, because we also get to see some questions in steam engines and steam turbines, and also relate them to all this. So in order not to get confused, we should stick to a convention that will let us or enable us to flow without any breach. So I will take this convention just like I said. I will clean this. Yes, and clean this. So that is it. I clean my teeth. So now let's take a question that will enable us to understand this. So now Here it goes. Example 1. In the compressed stroke of an internal combustion engine, the heat rejected by the cooling water is 45 kilojoule per kilogram and the work input is 90 kilojoule per kilogram. Calculate the change in specific internal energy of the working fluid and stating whether it's a gain or loss. Now, this is a simple one based on the formula we just derived. So, how do we go about this? It's so simple. You start by bringing out your parameters. So, parameters given here. Parameters given. Parameters given. The heat, but the heat is rejected. Remember our sign convention, just like I stated in the other page. So heat rejected, Q is 45, but minus since it's rejected heat, so minus rejected heat. So work input of course is work done on the system. Work input is supposed to be plus. Yes, there you go. So from first law, just like we derived from first law, we have that Q plus W is equal to U2 minus U1. So substituting the values into the equation, we have minus 45 plus 90 is equal to change in internal energy. So finally we have that change in internal energy is 45 kilojoules per kilogram. Yes, it's as simple as that, as you all can see. So it doesn't end there. They said we should state whether it's a gain or loss. So positive 45 means it's a gain. So you come here, you can choose to write plus 45. So by mathematics, you don't write it that way. 45 is already plus. So you write it this way. The internal energy is a gain or increase. It increases. Yes. So it's as simple as this. So this is very simple. We just wanted to use this to make an illustration and to check the sign convention, because it's very important that you stick and know the sign convention you're using. It's not so bad if you want to use Q minus W is equal to U2 minus U1, but your convention will change. So working on this convention, decided to solve an example, and this is the example. So we are going to move into the next phase. So let's see what we have in the next phase. Yes, the next phase is steady flow energy equation. Now, what do we mean by steady flow? What is steady flow? Now, for a flow to be called steady, the mass flow rate, okay, the mass flow rate remains constant and the same. Yeah, that is for a steady flow, the mass flow rate remains constant and the same at the inlet and the outlet, and the property, the properties of the fluid doesn't change at any given point in time. It remains the same too. So what do we mean by this? We mean that mathematically, if we have that from the first law, mathematically from the first law, we recall that recall that Q plus W is equal to U2 minus U1. Okay? But work done. Work done is equal to PV. Now, how is work done equal to PV? From our basic knowledge, we know that work is equal to force times distance. Okay? Yes. Work is equal to force times distance. Similarly, pressure on the other hand is equal to what? Force over cross-sectional area. Alright? Yes. Then that means force will now be what? Pressure times area. Now substituting for the value of force in work done, we have that work done is pressure times area times distance. So, which will give us pressure times volume, because area times distance will give us what? Meter cube. That is the volume. So that is how this was derived. So now recall that yes, from this equation, that dq plus dw is equal to du. Now integrating this, we have the integral of dq plus integral of dw is equal to the integral of du. Yes, we have that. So this means that this is q, once you integrate that, plus the integral of dw is equal to the integral of what? Du. But dw is equal to minus p dv. So integrating this and also integrating this from limits 1 to 2, we have that w is equal to, remember our minus sign, equal to minus v v2 minus v1, which will give us the work done is equal to work done will now be equal to pv1 minus v2. Yes. So substituting this into this, we have that q plus w, which is equal to the integral of this, will give us q plus w equal to u2 minus u1. Okay? Yes. Now we're almost there. Now, substituting what we have here now we have that Q will be equal to U2 minus U1 minus W. Now recall that we got W to be V1 minus V2. Okay, yes, so Q will now be equal to what? U2 plus PV2 minus U1 plus PV1. So of course the pressure, as you can see here, remains constant, but since we are dealing with inlet and outlet conditions, so permit me to write something like this so that everything will be even. Okay, yes, everything will be even. So but this formula is for what? A constant pressure. That is when you have the pressure doesn't change. But for inlet and outlet conditions, we have to indicate the inlet pressure and the outlet pressure. So having said this, we can go down and say, but H is equal to U plus PV. Then that implies that this becomes H2 minus H1. Now, having said this, we are going to use this to prove out the steady flow energy equation. So, how do we do this? From Bernoulli equation, that is from fluid mechanics, from Bernoulli equation, we have that this U1 plus C1 squared over 2 plus Z1G plus P1V1 plus heat. Of course, remember the formula or the definition. The mass flow rate doesn't change. So for the outlet condition, it becomes U2 plus C2 squared plus Z2G plus P2V2. Okay, that's it. So we have this. So from Bernoulli equation, we got this out of Bernoulli equation. This, because this is potential energy and this is kinetic energy. Okay, yes. So I'm gonna clean this right now, and arranging this, we have that M into bracket U2 plus C2 squared plus Z2G plus P2V2 minus M at the mass flow rate. It doesn't change, so we have this over here too. We have this over here. So that's right. We are going somewhere. Okay. Then further arrangement, we have this. Now time to gather the internal energy and the PV, the U plus PV, just like we proved up there. So we have something like this: 2 squared over 2 plus Z2G minus, arrange this 2 plus P1V1 plus C1 squared over 2 plus Z1G. Okay? Yes, we are going somewhere. We are about to get the final equation. The final equation. The final equation. This is H2 plus C2 squared over 2 plus G Z2 minus M H1 plus C1 squared over 2 plus GZ1. So finally H2 minus H1 plus C2 minus C1. C2 and C1 are the internal, they are the inlet and the outlet velocity. The inlet and outlet velocity. So we have these two, GZ2 minus Z1. Somebody might be asking, what's all this? Yes. Now, from this formula, this is the SFEE formula. Up here, we have gotten it. So this is our SFEE formula, which we'll be using to solve questions. Yes, this is it. We'll be using it to solve a lot of questions. Okay? Yes. So, but C2 squared minus C1 squared over 2 is the kinetic energy. The kinetic energy. Change in kinetic energy. Yes. Let's use that word. Let's use the word change in kinetic energy. Change in kinetic energy, while G Z2 minus Z1, GZ2 minus Z1 remains the potential energy, just like we said from fluid mechanics, that's from Bernoulli equation. Change in potential energy. Okay. Alright. We have proven the formula for the SFEE. So we are going to use it right away to solve a question. Yes. Be able to illustrate how everything works and how you'll be able to tackle questions once you see them. Questions under steady flow energy equation. So I'm going to take a question. Yes. Let's take a question. Example 2. In a gas turbine unit, the gas is flowed through the turbine at 17 kilogram per second. At 17 kilogram per second, which is the mass flow rate, is constant at both the inlet on the outlet condition. So, and the power developed by the turbine is 14,000 kilowatts. That's turbine work. The specific enthalpies of the gases at inlet and outlet are 1,200 kilojoule per kilogram and 3,000 and 360 360 kilojoule per kilogram respectively. Now, the velocities of the gases at inlet and outlet are 60 meter per second and 150 meter per second respectively. Calculate the rate at which heat is rejected from the turbine. Now, as you can see, this is a typical example of the steady flow energy equation. So, how do we go about this? First of all, you write your parameters. And how do we do this? You say parameters given, solution, parameters given, parameters given, parameters given. The mass flow rate, which is 17 kilojoule per second. The power developed by the turbine, that is turbine work, is negative. Remember, is power developed by the turbine. Remember we said whenever a system is doing work by itself, that means work is given out. And if work is given out, it's just like heat is being rejected, which is a negative too. So turbine does work on the surrounding. So work done by the turbine will be minus 14,000 kilowatts. Okay. Now our enthalpies is 1,200 kilojoule per kilogram and H2 360 kilojoule per kilogram too. Yes, we are going somewhere. Our velocities at inlet and outlet are this and this. Good. We are going somewhere. Now, let's quote the formula for the SFEE. So, the SFEE formula is given by Q plus W, which is equal to mass flow rate times change in the enthalpies, the specific enthalpies, plus the change in the kinetic energy. Remember, said that change in kinetic energy plus change in potential energy. So, but the change in potential energy was not given. So, you can say it's negligible or it's equal to 0. That is, it's negligible. Okay, so this is gone. So we now have Q plus W, which will be mass flow rate into H2 minus H1 plus C2 C2 squared minus C1 squared over 2. Yes, this is what we'll now be working with. This is what we'll now be working with. So they say we should find heat rejected. So normally how this works is at the end of everything, at the end of a question, the answer will determine if heat is supplied to the system or heat is rejected. So depending on the question, they asked us to find what the heat, the rate at which the heat is rejected from the turbine. Now, this is what we do. We have that this is minus. Okay, let's input all the values now. Okay, let's input the values. Let's input the values. Let's input the values now. So turbine work, remember, turbine work is 14,000 kilowatts, but I'm not going to write the kilo. I want everything to be in kilowatts. Okay, since everything is in kilowatts, we do it this way. So this is what 3,000 360 minus 1,200. 360 minus 1,200 times 10 raised to the power 3. Okay, so even here we are going to write that. Okay, if you want to convert to kilowatts, you can do that, but let's just maintain the standard form of solving things. So I'll say times 10 raised to the power 3. This space is too small. This space is too small, so I'll rewrite this. Stating that Q minus 14 times 10 raised to the power 3 is equal to this. Okay, then plus 1/2 times 150 minus 60 squared, close the bracket. So Q minus 14,000, that is 14 million now. If I add the kilo, will give us minus 840,000. Okay, because of the kilo down here, the 10 raised to the power 3 plus, after doing this, you have that we have 9,450 as the answer for whatever change in kinetic energy is. So simplifying further, we have that. Okay, we have that. This will give us minus 14119,350 watts. Okay, because it's a watt. So heat now will be minus 14119.350 plus 14000, that's 14,000. Now this has been converted back to kilo the way it was before. So to maintain, because power is actually stored in kilowatts, so not in watts, so we maintain the SI units. So solving this, finishing up, we have that this is this kilowatts. Now, as you can see, they say we should calculate the rate at which heat is rejected. The answer has come out and there's a negative. So the negative sign denotes, okay, the negative sign denotes the negative sign, okay, the negative sign denotes that heat is actually rejected. Negative sign denotes heat rejection, or the negative sign means heat is being rejected. So guys, we've solved an example to help illustrate and help you understand how the steady flow energy equation works. So see you in the next video. Stay tuned. I remain Daniel. Thank you.
It leads to liquor on some ladies. Yeah, we did turn up on a daily. It's how I walk up. Yeah, soft walk.